I am Jennifer DiMatteo, a technical consulting engineer, and what Kevin and I do as on our team is provide support for the Intel analyzer tools that are part of the OneAPI and Intel Parallel Studio packages. And those tools include Vtune, Profiler, Intel Inspector, and Intel Advisor. And we provide trainings, do documentation, and handle support tickets and anything really related to customer usage of our tools. So in this workshop, I'm going to show you how you can use Vtune Profiler to analyze your PMDK applications and find issues related to the use of persistent memory and how that can be improved, or any other issues regarding the persistent memory within your application. So the first sample that I'm going to show you is the matrix sample, which is our tried and true way of highlighting performance issues that Vtune Profiler can show you. So, you know, it's familiar to most people. It's easy to understand, and we can really change it to highlight whether you might have memory issues, CPU issues, threading issues, things like that. So I am going to walk through that sample and show, you know, not only how you can see original problems with PMDK or persistent memory usage, but then also what it looks like once you fix some of those issues. So first I'll do that. Secondly, I'm going to show a sample that's included with the PMDK examples on GitHub. And this is the word count with using MapReduce. And I'm going to show a few different analysis types that that show you utilization of the persistent memory with that particular sample. And following that, I'll go through some additional Vtune usage and answer any questions that have accumulated over the presentation. And Kevin is also going to ask me questions while I'm doing the demonstration, so so that you can get, you know, quick answers to those, and I can explain them in the context of what I'm demonstrating. So I don't want to come back to the slides, so I'm going to next, well, first review the matrix sample, and we do have a link to a cookbook recipe for Vtune on looking at the persistent memory overhead. So you can take a look at that if you want to review this process on your own. And following that is the word count sample I mentioned. And it is, as I mentioned, in the GitHub repository under the PMDK examples. And for more detail on what I did to run the collection on that, that example, I created a folder containing some text files, about 200 of them, each around 1 megabyte. And then I created a script that would do both the loading of those text files into a persistent memory object on the in the persistent memory, and then after that, it actually runs the MapReduce for the word count on that persistent memory object. So both of those steps are included in the results. And as I mentioned, I created a script, and then I just ran that script with Vtune with this example of collecting the memory access analysis. So now I'm going to do the demonstration.
So Jennifer, we have a couple questions before you get started. So a couple questions just related to interrupting DC memory in general. So the first question is, can Vtune also be used with interrupting DC memory mode?
Yes. So you can use Vtune to look at a number of different memory issues. So there's the memory access analysis, and there's the overall system analysis, and there's also a storage I/O analysis that you can use to collect a number of different configurations of your platform.
Okay, the next question is very similar. It says, should I use that memory mode or should I use app direct? So I think I'm going to answer this question because when you're asking should I use one mode or the other, the answer is it's very, very application dependent. The beauty of memory mode is it lets you try it out without making any code changes at all. With app direct, you really need to choose wisely to get your performance. I think that's it for now, Jennifer. Thank you.
Thank you. So first, let me bring up my, so this is the matrix sample that I mentioned, and there are several results here, and all of them are using the memory access analysis. So I'm going to open up these in kind of the order in which the application was optimized. So here I'll open up the original sample, results for the first iteration. Here you can see.
So there's another question about analysis types in Vtune. So you mentioned memory access analysis type. Is there any other analysis types that you recommend?
Yes, and the next sample that I'm going to show is uses two others. So what I can show quickly is, and of course, when you're trying to investigate memory issues, using the memory access analysis is going to trim out some of the other events collected that aren't related necessarily to memory utilization, because if you if you run the microarchitecture exploration, for example, you get a lot of data, but you're also collecting data on your front-end bound, your CPU data. So there's a whole bunch of events, and the memory access really targets memory usage, memory bandwidth, and gives a view of your bandwidth over the persistent memory, over your UPI if you have a two-socket system, and DRAM. So that's why when there's a memory issue, starting with the memory access is probably going to be the most helpful once you have narrowed it down. So that's why there's a focus for this sample on the memory access.
So along the same lines, there's a question here that says, if I am on a multi-socket machine, can Vtune be used to catch potential new issues with persistent memory?
Yes.
I think that's it for now. Thank you.
Thank you. Okay, so first, looking at the summary for the memory access analysis here, and looking at this, the memory access, you see that it's really focused on memory. There's no extra information that's not going to be useful when you're focused on looking at memory issues. So at the top, you see the elapsed time. That's the total time that the collection was run. So that's almost a little over 5.5 seconds. And then the CPU time here is the total time over all of the CPUs that the application ran. So this would be ideal if you're concerned about utilizing all of the available CPUs on your system, then this should be close to a multiple of the elapsed time and the total CPUs you have available. But that's, you don't always want to use all of your CPUs. Was there a question?
There's actually a question about you're showing the metric memory bound. So what does memory bound mean? And if I am persistent memory bound, what should I do about that?
So memory bound is the number of, or the percentage of instructions that were stalled due to memory loads. So when you execute an instruction, it needs to pull the data from memory, or it needs to get the data, and if it's not able to execute because it doesn't have the data immediately available from memory, you're going to see a high, or it's going to add to the number of misses or stalls due to memory. So this is high because of loads from memory not being optimal.
So on the same token, then persistent memory bound would mean you were stalling because of persistent memory as opposed to just memory in general.
Right. So, and one of the things that Vtune is great at is providing help within the results so that you can immediately see what the problem is, and it even gives you tips on how to improve the result or what to do next. So that's really helpful. And then having the flags, Vtune has a threshold at which point a metric is too high or too low, and at that point it's going to flag it as a potential issue that you should investigate more deeply, and at least from the summary page. And then there are other ways that Vtune will pinpoint metrics that it finds might be leading to bottlenecks in your application. So this is actually a hierarchical view of the memory issues. So it starts with overall memory bound, and then goes through the local cache levels, and shows you the percentage that those are bound, and then you can see if you're DRAM bound, which this isn't using any DRAM, or isn't bound by DRAM here. And then you can see that it finds that it's persistent memory bound. It's not bound by bandwidth. In fact, if we look down here at the bandwidth utilization histogram, this is showing the times, the amount of time that bandwidth was utilized at different values. So it's got it's extreme. Well, actually, I should be on the right one. This is DRAM actually, so there's no DRAM bandwidth that it's showing, but you can actually go look at your persistent memory and then see here the bandwidth utilization at 12 for 3.5 seconds of the workload. It was using this amount of bandwidth, which is low. So there's no issue with bandwidth utilization, except that it is low and maybe not effectively using the available bandwidth for persistent memory. But here we can see that it's not bandwidth bound, but it's still bound for loading from persistent memory. And then you get to see the number of loads, the number of stores, the last little cache miss, and all of those are due to local persistent memory accesses. And then you can see the average latency, the cycles spent for the memory accesses, the total thread count, and pause time. So I explained here the bandwidth utilization histogram, and then you can also see here the top memory objects by latency. So we can see the one thing about the memory access analysis is you're able to collect on memory objects and get details not only at the function level, but at the memory object level. So in this case, we can see some of these memory objects, and then which ones are actually high latency, so we can really identify where, which allocation is causing a problem, and then maybe tune our data structure to, or how the array is iterated through to have faster accesses. And then there's a latency histogram here as well. So I'll go into the bottom-up view. And here you can see the bandwidth over DRAM, and there's minimal. And then the persistent memory bandwidth. So here we can see that it's low with primarily writes. So that dark blue portion, as you can see here, is writes, and then the kind of light teal part, that's reads. So it starts with low, and then it gets a little bit higher at the 2-second mark with mostly reads, and then it's still some writes happening. So that's a good way to view how our persistent memory is being used. And in this case, it was being used over a single package, whereas there are two for the DRAM bandwidth.
We have a question on package. Can you explain what does package mean?
Sure, that's actually like the socket. You can also call it. So on this system is, we can actually see what the system was that we use. This is actually a 2-socket. I believe it's a 2-socket system. It doesn't actually show this the CPU, or actually there's no UPI here, so I think it is a single. There's just two packages for bandwidth, but it's just refers to 2 sockets. So on for CPUs, so if you have two separate, I guess, packages for DRAM or persistent memory, then you'll see them listed here. Or if you have two CPU packages or sockets, then you'll also see a UPI bandwidth going between each CPU socket, and then the DRAM packages. So that's kind of, and then you can see the channels also for each package. And then looking at this grid below, you can, it's sorted by CPU time, and then grouped by the function and call stack, which memory access analysis doesn't allow collection of stacks, but you can actually change this group here to get a better idea, or view the data in a way that makes sense for the collection you ran and the information you're trying to get to. So we could actually look at group by function and memory object as well, and see that here we have our main function, and then it's the vast majority of CPU time for the collection, and then it has these values for memory usage, and the pink highlight means that the value is over or under some threshold that is programmed into Vtune, and it also considers the amount of time that this function spends on the CPU. So for very short running functions, with regards to the overall collection, it's not going to highlight high values, because there's not a benefit really in trying to optimize for that, because the function doesn't consume a big part of the overall workload. So, like for example, in this case, it says 54%, which would normally be very high, but for only running 0.2 seconds, it's not worth optimizing this. This is where the focus should be, and the focus, here is for the persistent memory bound metric. So here we can see the number of loads and the number of stores, and then we can also see the local persistent memory access count, the average latency for the memory accesses for this function. And then we can also look at the individual memory object here, and look at them in terms of their loads and stores. So for example, these two allocations have a big number of loads but not stores, and it's this allocation here that has that's doing the vast majority of the stores. And these gray values here just indicate that not enough samples were collected to make it a reliable reliable metric. But when it's, when the values are this low comparatively, we can focus on the what Vtune considers the reliable metrics.
So Jennifer, we have a question about loads and stores. So which ones are faster?
So loads are going to be faster for writing to persistent memory is not going to be fast. I mean, ideally you want to do your loads, and then your stores can go to DRAM, or there's not much value in writing back to the persistent memory when you're just storing your values. So we can see that there's we can see that the memory access count by the particular allocation as well, and the average latency, and get some more of those details for each of these memory objects. So let's go to since it is doing quite a few stores here. One of the things that could provide value is if we're only doing if we're only reading, and that's what the next result is going to show for read only for this this same matrix workload. We can see that by doing that, the elapsed time is now a little over 2.5 seconds versus the over 5.5 that it was. And then we see that the persistent memory bound value is still roughly the same, near 20%. But now there's an increase in the persistent memory bandwidth bound. So that means that it is actually utilizing the available bandwidth, and we can see that reflected in our histogram here. So whereas before, I think it was right around 12 for the most part, we can see that there's a high number of 24 here, still short of the maximum of 60, but an improvement because we're getting more data that way. So we can look at we can view what that looks like in the bottom up. And now we see there's still that portion in the beginning where it's doing some writes, but then when you go to the second half, it's all just stores. There's no or it's loads. I'm sorry. The stores are now being done on DRAM. The writes here with some reads because it's still using the value that gets stored, but it's going to be faster over DRAM. So here we can just read and then still do the faster processing over DRAM. And we still have the the grid here that we can look, and we can actually still look by the memory object and function. So we see that it's still persistent memory bound. We still see our loads and stores. These don't really change. It's just now the stores are being done over DRAM versus persistent memory. So persistent memory is great for looking at data that's not in storage, but allowing the DRAM to do what it can as well, will lead to better performance, as we can see here in the greatly improved CPU time. And then we can also take a look at any other issues that might be causing performance bottlenecks. And one of the things was that it's not vectorizing optimally, and that's, if we were to look at the code, we can see how those, I'm not sure if I have the source available here. I do. So that's one of the other nice things about Vtune that I want to mention is if you double click on one of your functions and you have set up your Vtune analysis to point to where your sources and binaries and symbols are, then it'll be able to resolve the code so that you're able to get to the particular line of code that has these issues. So let me bring back that code here. So here we can see, here is the line of code, and where the issues are, which can be very helpful. And if you wanted to look at the assembly level, you can see the actual instructions that are being used. So,
Jennifer,
yes,
we have a question about vectorization. So Intel also has another tool called Advisor. So how does Vtune compare with Advisor?
Vtune will allow you to see the instructions that have been run and whether they are at the assembly level. You can see, whether your instruction is a like a SIMD instruction or a vector instruction. It doesn't really provide insights into what the compiler did to vectorize. It can show you for floating point operations whether they're scalar or packed. So packed means that it is using some vectorization, and then scalar is not vectorized. So that's kind of the extent that you can determine vectorization. So if we were to look at, and I'm not sure actually if the memory access analysis will provide the has the, or collects, I guess, on the events that are for the floating point operations. I don't see them here, but that's basically all it's going to do, is show you, that level. What Advisor does, though, is it can analyze the application and show you, why, if it wasn't vectorized, and it shows you this in a very, should I say, intuitive, I guess, format, where you're looking at your loops, and for each loop it's showing you whether it was vectorized, and if not, why it likely wasn't, and then if it was it using the best instruction set, anything that might be preventing it from getting the optimal, I guess, vectorization, because you can vectorize, and if you still have poor memory latency, then all you're doing is running those instructions, I guess, faster, but you're still having to wait for memory. So you're not necessarily benefiting by vectorization if your memory accesses are very slow, because it's not necessarily going to improve that. So looking at fixing your memory accesses first is the best place to start, and then go and see how you can improve the vectorization. And that's another thing that it shows, is Advisor, I should say, shows is the memory access patterns. So that's going to be, stride information. If you have a very long stride, then it can be the reason it's not being able to get memory from a local cache and has to go out to DRAM or persistent memory, because it can't. It has too big of a footprint to fit in the local caches. So that's another great feature of Advisor. But coming back to Vtune, we can look at the instructions that are being run and see, the potential for further improvement. And that's where, sorry, I thought I was looking at the source code here. But actually looking at the platform is also a good view, because you can see by your threads kind of just all of the system level details in this in a bigger format here. Let me go so I don't run out of time here. I'll go to the next step, which is the default vectorization. So we can see that it's still maybe actually the amount of persistent memory bound is even higher here, and that's where we want to just make sure that our accesses are as fast as they can be for the vectorization to really make a good impact. And as I mentioned, running out of time, I think I've shown some of the ways that you can look at the persistent memory usage and improve it. I want to go to the other collections that I ran on the word count sample. So I'll just close these. Actually, I can go to the welcome, and then I'll go to my my other project. And I mentioned starting out with the memory access analysis, since this is looking at memory utilization, but I also took a couple other collections with different analysis types to show the difference in what you're able to see. So in this case, we have 47% memory bound. There's a high amount of DRAM bound, and then memory bound is here about 13, persistent memory bound about 13%, but it's not bound by bandwidth. And we can see here what our bandwidth utilization looks like for persistent memory as well. So going to the bottom up. So this is running over, we see the two packages here. So this is this is running over both sockets. There hasn't been any pinning here, and then there is an available persistent memory node, but we're not using it. Only the one package 0, and then there are two DRAM packages, but it's really just using package 0 with just a little bit over package 1. So we can take a look at how, the top function, and I did not collect the memory objects for this particular workload, but you can see the top function, that it's DRAM bound, and this isn't the function that is persistent memory bound. That one is actually this this string length function, that it's memory bound and doing a lot of loads. So and then there's a sort here that's using a lot of DRAM. So that's, we can see, take a look at our different memory accesses and how we would want to improve the way that we access memory to improve performance. And what I want to show is, since there was a question about collecting with different analysis types, I wanted to just show a comparison of what it looks like when you collect. For example, hotspots is one collection that we tend to recommend in general as a starting point when you're using Vtune to profile your application, because it's going to give you threading information and your clock cycles per instruction, so you can go into one of the deeper analysis types. So it's a bit higher, or I should say less overhead, where in some cases when you're running the microarchitecture analysis or the memory access analysis, you have to be careful to tune the collection to collect on the right parts of your workload, so you don't end up with a huge result set, because as you do want to collect all the data you can on these newer servers with 96 cores and a number of threads running over them, it can really generate a lot of data when you collect. And then that increases the time it takes to post-process and finalize the data and resolve your symbols. And then when you actually go into using Vtune, the process of filtering and sorting can be very slow over huge data sets. So, you know, a high level look can really help you figure out where to go next and maybe, you know, what to focus on.
Jennifer, we have a question about, is there a way to reduce the amount of data that's collected?
Yes, so that's one of the things that I ran into doing the memory access analysis for this word count sample. I'll show you the analysis configuration, and that's one of the reasons why I didn't opt to analyze the dynamic memory objects, is because it was collecting far too much data. But another thing that you can do is adjust the CPU sampling interval. It defaults at 1 millisecond, which for some workloads can be too low, causing more frequent sampling. And if you want to run a collection over a longer period of time, it's better to increase this. You know, the other considerations are, if you have a lot of short running functions, the 5 millisecond may be a little high. So if you still want to keep it at 1, then you can try to shorten the amount of time that you run a collection. We also have an API that Vtune uses that you can tell Vtune when to collect and to pause the collection within the code. So if you really want to narrow down where you're collecting, you can use that API to say, I only want to collect on this set of functions, or you know, in this time frame, so that you're not collecting maybe on parts of the workload that aren't of interest.
I also wanted to mention that you also have the ability to use the CPU mask feature in Vtune. So if you know which CPUs you're running on, you can tell Vtune to only collect on those.
Yes, so that's another thing. So that is especially valuable with especially with HPC workloads, where you generally have a number of worker threads all doing the same work over a large number of CPUs. You may not be interested in seeing, you know, the same results many times. If you know where your main thread is running, and you know, collect a smaller sample of the worker threads, then you can specify just, you know, which CPUs you want to collect on. There's no way to say to specify what threads, because Vtune doesn't know anything about that at that point unless you use the API. But you can set that here, and you can also one thing is, if you have a longer running workload, but you're waiting on a certain event to happen. Actually, let me bring this up in the analysis configuration so that it's a bit easier to see. It's not all grayed out. And at this point, I'll also mention this arbitrary host. I think I've seen confusion as to what this means. What this does is it allows you to generate a command line, because you know, Vtune has a lot of knobs, there's a lot of settings, and looking through the graphical interface, it's pretty easy to toggle what you want to collect and set the settings. But you know, I'm running this in Vtune. If I were to just try to generate a command line by using the local host, that's not going to be really work for Linux, because it's going to generate a Windows command line, and maybe I'm running on an old Haswell, but my server is a Skylake. So this lets you generate that command line for the system that you want to run on without having to go through the documentation and find all of the different knobs that you need to set for your configuration. So you can enter the application you want to launch here, or if you want to attach to a running process, you can do that as well. Just or you can even leave it out if you want to fill it in later. And here's the advanced section where you can try to target the collection or at least configure the collection size a little bit. You can resume after a number of seconds. So if you have, an initialization phase that you don't really care about, you can skip past that and enter a number of seconds there. You can stop a collection after a certain number of seconds, and that's, you can also do that if you're running through the GUI. You can do that. With the buttons here, and you can just stop it and start it paused. But if you are generating a command line, you'll want to configure that here. You can change what child or specify what child processes you want to analyze if you don't want to analyze all of them. You can analyze system-wide if you want to see what the whole system is doing as your workload of interest is running. This is a little bit different than collecting.
Jennifer?
Yeah.
We only have a few more minutes, and then we do have a couple questions that have come in. So just a couple questions about, are there any other tools that can help with persistent memory?
Yeah, so we do have Intel Inspector. So and it has the persistent inspector that can help you correct problems with your application, so that as Intel Inspector, the regular version can identify memory leaks and threading deadlocks and the like. Persistent Inspector will help you identify when you're going to utilize persistent memory in a way that's going to negatively impact your data and overwrite. Make sure that things are going to run in the correct order so that you get the results you expect.
So we have a question about Vtune Platform Profiler versus Vtune. Which one should I start with?
It depends on, I guess, what you want, what you're trying to collect. So Platform Profiler is looking at the system level and how your overall, all of the applications on your system are utilizing the hardware. So it's not looking at particular processes. It's just looking at that high system level, and it has the benefit of being able to run for longer periods of time than Vtune, because it's not collecting the process level details. And I look at it as using Platform Profiler to tune your hardware for your software, and Vtune Profiler as tuning your software for your hardware. So it depends on what your goals are.
Okay, that sounds great. So I think that's probably all we have time for. Yuri, did you want to mention any final comments?
Yeah, no, I want to thank both Jennifer and you. For everybody, we had a lot of engagement, a lot of great questions. We'll reach out to the to the people that asked the questions we were not able to answer here. Jennifer and Kevin are experts on this. Feel free to reach out via LinkedIn or via communication through the conference. Their bios are in the speaker section. And thank you very much for attending.